Okay guys, we did question number 3, and the next thing is to find, comparing two complex numbers if they are equal. So if two complex numbers are equal, then their real parts have to be equal as well, and the imaginary parts must be equal as well. So if Z1 and Z2 are equal, then the real part of Z1 must be equal to the real part of Z2, and the imaginary part of Z1 must be equal to the imaginary part of Z2. So on the basis of this, given question number 4. On the basis of this, let's do question number 4. So can you simplify the left side and bring it to the a plus bi form? A plus bi form, and Daniel, just take the red light on the side. It's on. Okay, so left side, bring it to a plus bi form, and if it's saying that it is equal to 8 minus 39, that means the left side real part must be equal to the right side real part, and the left side imaginary part must be equal to the right side imaginary part. So if we bring this to the a plus bi form, this is what we get. So if both these complex numbers are equal, that means x plus 6 must be equal to 8, which implies that x equals 2, and 2 minus 10y must be equal to minus 30. So 2 minus 10y must be equal to minus 30, which implies y must be equal to 3 by 2. One more time. Check. Right? Are we good? Any questions? Can I go on? Okay, now this concept will help us find the square root of a complex number. Basically there are two methods, but I am doing the standard one first, and then we will come down to the other one again when we do the exponential form. So let's say this is the question. You are asked to find the square root. You are asked to find the square root of 5 minus 12y. Now, if you are asked to find the square root of 5 minus 12y, that means square root of 5 minus 12y. Oh, I'll just put the plus minus on one. Square root of 5 minus 12y must be equal to some complex number a plus bi. The result must be equal to some complex number, right? Square root of a complex number would be another complex number. Has to be of the a plus bi form, and plus minus 2 square root you should be getting. Now if this is the case, then can I say that 5 minus 12i is equal to a plus bi whole square? Can I say that?
Yes.
Now this is the basis on which I am going to find out the square root of 5 minus 12. And this is standard procedure. This is your step 1. Equate the complex number to a plus b whole square. And how it becomes a plus b whole square, you know, through this it becomes a plus b whole square. So this is your step 1. And this is what I have clearly stated over here. To find the square roots of complex number z in the a plus bi form, consider root of z equals plus minus a plus bi, and therefore z is equal to a plus b whole square. And this is what will lead you to the square root. Okay, so what do we do then? You open the bracket and then you compare with the left side. So there will be an a plus bf form on the right side, there's 5 minus 12 on the left side. So you compare, both sides are equal, therefore the real parts must be equal, the imaginary parts must be equal. So this becomes a square plus 2abi plus bi squared. You know bi squared would be b square I squared, and I squared is a minus 1. So this becomes a minus b squared. Are we okay with that? Plus 2abi. So this is your real portion and this is your imaginary part. And you see both complex numbers are equal. So if they are equal, that means a square minus b square, the real part must be equal to 5, and 2ab, the imaginary part must be equal to minus 12. The same concept that we did in the previous question. When two complex numbers are equal, then the real parts must be equal and the imaginary part must be equal. It's like comparing coefficients in case of polynomials and other equations. Now, from here I can say AB is equal to minus 6, and I can say that B equals minus 6 upon 8. Is that fine? And I can use this here, solve the two equations simultaneously. Replace the B by minus 6 by A squared equals 5. If you simplify this, I think you will get a disguised quadratic equation. Check. I hope you're getting this. Now don't get started with the a power 4 because it's a disguised quadratic. There's an a power 4, there's an a square. So clearly it's a disguised quadratic, we can easily solve it. So let a square be x, or whatever variable you want to take. So x square minus 5x minus 36 equals 0, which means you get the value. You get two values of x. Check.
9 and minus 4.
9 and check, we are getting 9 and minus 4. Any questions still here? Now, if you remember, we had this discussion and I very clearly expressed something. I'm just going to go back to that. When we were discussing the basic a plus bf form, I very clearly said that a plus b is a complex number, a is the real part, b is the imaginary part. bi is an imaginary part is because the I is attached with the b. Although a and b number-wise they are real numbers, a and b themselves are real numbers. This is when you attach an I with it, it becomes an imaginary number, and if you add it to a real number, the whole thing becomes a complex number. So, if you say x is equal to a square, then a square can only be equal to 9. It can't be equal to minus 4 because a itself is a real number. A square cannot be minus 4. So, a square is a 9, which implies that a is a plus minus 3. Are we okay with that? Now you're getting two values of A. And yes, you should be getting two values of A because therefore you'll get two values of B and you are supposed to get two square roots. So if A is 3, then B is, your B is minus 6 upon 8. So A is 3, your B is minus 2. And if your A is minus 3, your B is plus 2. Which means the two answers that you're getting the two square roots of 5 minus 12i are 3 minus 2i and minus 3 plus 2i. Or in turn you can say plus minus 3 minus 2i. You can just write it as plus minus 3 minus 2i, or you can just write it as plus minus 3 plus 2i, the same thing. You can use square roots.
So could you scroll up a bit?
Count it. Is everyone okay till here? Any questions? Okay, so this is a standard procedure. This is your step 1. Your step 2 is expansion, and then comparing. That's your step 3. Comparing real parts and imaginary parts, and therefore that after the comparison you will get your values of A. The minus, ignore the if you get 1 minus, because A square cannot be minus 4. So from this one value you will be getting the 2 answers. Are we all good? Any questions? Is everyone okay with the procedure? Okay, and I need to repeat this statement, although I've said this before, but it's very important. Remember, the complex roots of a polynomial with real coefficients always occur in conjugate pairs. We had a discussion on this that if एक root 2 plus I is considered, there has to be a 2 minus I as well. If one root is 3 plus 2i, then there has to be a 3 minus 2i as well. If the polynomial that you're solving has real coefficients. If the coefficients are not real, then it can be anything. Which means this, that if you look at, if you look at question number 6, it's a cubic equation. Question number 6 is a cubic equation. Now, it's saying, so if it's a cubic equation, we're expecting 3 roots. Okay, now it's saying that one of the root is a 2 minus I. Now, if one root is a 2 minus I, then there has to be a 2 plus I root as well. Because the polynomial has real coefficients. So, if one root is 2 minus I, there must be another root to the polynomial which is 2 plus I. Now, there are only 3 roots. 2 of them are complex. The third one cannot be a complex really. Because if the third one is a complex, then there has to be a fourth one as well. A pair of the third one. So, and that's not possible because there are only 3 roots here. So, the third one has to be a real root. And that's what they're asking. By the way, this is a mistype. Find the real root of the equation, not the real roots. Find the real root of the equation, given that one root is 2 minus I. So, if one root is 2 minus I, we know the other root is 2 plus I. Now, how do you go about finding the other root? Even for like standards, this is a standard procedure question. It's a very basic question. The thing you need to do is, one thing is, you can use hidden trial. That's the standard way. A general method that you did in the first chapter when you did polynomials. You make factors of the last one, and you try all of them. One of them will give you 0, and that is going to be a root. That's one way. But I really don't recommend you do that here because there are too many possibilities here right now. And I just want to discuss the other method at the moment. So the other method is, which is better method in this case, is you make a quadratic factor out of these two roots. And to make it into a quadratic factor, I need to bring back that thing that I said last year about quadratic equations, and it's a property of quadratic equations that x squared minus sum of roots coefficient of x plus product of roots. And I also showed you last year that you can directly form an equation from the roots. If you know what the roots are, you don't have to go through the procedure of multiplying, making them into factors, multiplying, and then going back to the main equation. I'll give an example. Let's say the two roots of an equation are 2 and 3. There is a quadratic equation जिसके दो roots हैं 2 and 3. What is that quadratic equation? Now you can directly find the quadratic equation, and I know that the quadratic equation is x squared minus 5x plus 6. Now how do I know that? I know that because the coefficient of x has to be the negative sum of the roots. The sum of these two roots is what? 5. So the coefficient of x has to be minus 5. And the last constant has to be the product of the two roots, which is 6. So the last constant has to be 6. So the equation has to be an x squared minus 5x plus 6. Can't do this. This is a core property of polynomials. Because you only deal with quadratics, you just need to know how to quadratics. So you can use this to directly get the quadratic factor out. What is the sum of the roots here?
Minus 4. Positive 4.
No, sum of the roots is plus 4. So the coefficient of z would be a minus 4. I'm finding the quadratic factor, so it has to be in the z squared form. So z squared minus 4z plus, what do you think is the product of this? Now if you remember, any complex number multiplied by its conjugate is just simply a square plus a square plus b square. Any complex number multiplied by its conjugate is a square plus b square. And we did a question on this. This is rule of thumb. The minus goes on because of the I square. The minus goes on because of the I square. So this will become 2 square plus 1 square, which is 5. This is your quadratic factor. Z square minus 4z plus 5. The sum of the roots, negative sum of the roots, and the product of the roots. Multiply these two, you should get a 5. Add these two, you should get a 4. The z coefficient has to be the negative sum of roots. Negative sum of roots. You can directly form the quadratic factor. Are we good? Now once you have the quadratic factor with you, now you can get the one factor out, because it's a cubic, you know the other factor is a linear factor. You can just simply use equating coefficients and get the answer. Now this has to be equal to z square minus 4z plus 5 into the other quadratic factor, which I don't know what it is, but it has to be
minus 2 of
az plus b4, the general form. Now you can just compare coefficients and get the answer.
x is minus 2 over 3. Minus 2 over 3 x.
Okay.
The value of z.
Now, to compare coefficients, if you remember, I gave you a shortcut. You don't have to completely multiply and expand the entire expression. Don't waste time doing that. You just need to find a and b. You can easily find that. The leading coefficients multiply to give you the main coefficient, and the last constants always multiply to give you the last constant. So 1 times a is a 3. So a has to be a 3. And 5 times b gives you a 10. So b has to be a 2. That means the other factor is a 3z plus 2. If I equate it to 0, I'll get the value of z out. That means the real root is minus 2 by 3. So you don't need to expand and equate coefficients. You can simply find the, because luckily the variables are in the first and the last position.
And we just use a calculator. We just use a calculator to take out the.
You have to show some working to show that you've done something. If you're doing the working anyway, so you check your answer, it's simple like that.
Working again, Martin.
Are we good?
Final answer खाली -2/0.
Yeah. The question is find the real root. This is the real root. That's the final answer. We were hunting for the real root. That's -2/3. Are we good? Any questions? Just fine. By multiplying these two. A minus b into a plus b is a square plus b square. So 2 square plus 1 square is fine. No. It's just a square plus b square. B is 1. So it's a square. I mean, you can take a minus 1 square root of c plus 2. It doesn't make it. Are we good? Any questions? Okay, there is a mistype in this question, so I'll get back to this later. Question number 7, there is a mistype somewhere. So we'll move on to question 8 for the time being. I think the first part you can do very easily. You just have to show that 1 plus side to the power 4 is equal to -4. That shouldn't be a problem. Just use simple binomial expansion. A plus b to the power 4. Just use simple binomial expansion, you should get the answer -4.
Plus I power 4.
A plus b power 4. Let's expand this.
AS वाली बात हो गई
Power 4 and a square.
वो थी ना तो पहले पावर इस करते हैं प्लस एनसीबी की बात है ये बात
Same thing, it's the binomial expansion.
Can we do it with the V2 method?
It's the same binomial expansion.
Yes.
You can do it by n. I mean, 4c1 is n, and this is n into n minus 1. You use the same, it doesn't matter.
वो है ना A2 वाले माइनस करके
The one that you've done in A2 is the general one that you can use everywhere.
हाँ
This one can only be used for a integer power. Positive integer power.
4i squared, 6i squared.
Yeah, yeah,
I square minus, and I cube is I square into I. So an I cube is a minus I. I hope you are okay with that. I cube is I square into I, which I believe is a minus I. So this would become a minus 4i. And an I to the power 4 is I square into I square. Minus into minus plus 1. So check, your answer is a minus 4. Are we good? Now, hence find all the roots of this equation. C to the power 4, b to the power 4 plus 4 equals 0. Now, how can we use this information to get the roots for this one? Yes, this implies that z to the power 4 equals minus 4. And we just agreed on the fact that 1 plus I to the power 4 is equal to minus 4. Which means one value of z is definitely 1 plus I. Because we just agreed that 1 plus I to the power 4 is a minus 4. And here you are saying z to the power 4 is a minus 4. So what value could z have? Definitely 1 plus I is a value.
1 minus 5 is minus 1.
Now, yes, because it's a polynomial with real coefficients. So if 1 plus I is a complex root of this polynomial, then the 1 minus I should also be here. Now, this is what we agreed on just now. We proved that 1 plus I to the power 4 is a minus 4. Now here we are trying to solve this. This statement means z to the power 4 is equal to minus 4. Now z is the variable whose value I'm trying to find. So if z is 1 plus I, then 1 plus I to the power 4 does give me a minus 4. That means z's value is 1 plus I. So if z has a 1 plus I value, and because it's a polynomial with real coefficients, that means there has to be a conjugate root as well. So the other root has to be a 1 minus I. Now it's a 4-degree polynomial. We found 2 roots. There are 2 more roots left. Now either both roots are real or both roots are complex. That we need to find. And that we can again find out the way we did question number 6. You make a quadratic factor out of this. Make a quadratic factor out of these two. So it's going to be z squared minus sum of roots. What's the sum? Minus 2z. And what's the product? 1 square plus 1 square. This is the quadratic factor. Use this quadratic factor to get the other quadratic factor out. And once you have the other quadratic factor, we'll break that up and see what the other 2 roots come out. So your polynomial is z power 4 plus 4, which should be equal to z squared minus 2z plus 2, and must be multiplied by another quadratic. So you know that the other one has to be a quadratic as well, because 2 quadratics will multiply to give you z power 4. So the other quadratic is an unknown. So let's say it is az squared plus bz plus c. Okay, no worries about A and C. We can easily find the values of A and C by just comparing. A times 1 should give you a 1. So A is definitely a 1. And 2 times C gives you a 4. So C has to be a 2. Now it's only a matter of B. Now for B you will have to make an expansion, but again you don't have to expand the two brackets completely. You don't waste time doing that. You've done this in the first chapter of polynomials. You just have to expand one term. Now you can decide whether you want to go with the z squared term or the z term. You just have to multiply those terms that give you a z or a z squared, whichever one you choose, and compare it with the left to get the answer. You want to go with the z squared or the z? Z squared? Okay, let's go with the z squared. So how do you get the z squared? You will multiply az squared by 2. So this multiplied by this, so that's a 2a. And other z squared will come out by multiplying bz by minus 2z. That will be a minus 2b. And equating it to the z squared term on the left. Is there any z squared term on the left? No. That means the coefficient is 0.
Sir, C, Z square.
Yeah, the C also. Sorry, I forgot. Yes, C times C. So there's a plus C as well. And this equal to 0 because there's no z squared term on the left side. Now, I think we already know the values of A and C. A is 1 and C is 2. So I guess your B value is 2. Which means the other quadratic factor is a z squared plus 2z plus 2. This now needs to be solved to get the other two roots out.
Minus 1 plus under root.
So whether you use the middle term or whatever, I don't know, because you might be getting complex roots. So just to be the safe side, use the quadratic formula. And what are we getting?
Minus 1 plus iota.
Minus 1 plus iota and
Minus 1 minus iota.
minus 1 minus iota. These are the other two roots. So if you completely solve, if you say hence find all the roots of the equation, then all the roots of the equation are minus 1 plus I, minus 1 minus I, and the other two that we found were 1 plus I and 1 minus I. 1 plus I and 1 minus I. These are the four roots. Are we good?